today we're going to talk about slow queries. And in particular, we would like to share with you some lessons learned building some query acceleration techniques shared between Grafana Mimir and Thanos. My name is Marco. I'm a software engineer at Grafana Labs.
Hello, my name is Susana, also a software engineer at Grafana.
Now, this topic is not new. Actually, 3 years ago, Tom was on the stage of KubeCon, North America, to present what I think at that time was the first query acceleration technique in Cortex, which is the range query time splitting. We will share in details later on how it works. And this talk is a sort of follow-up. So, fast forwarding 3 years later, what's the current state of the query acceleration techniques we use in systems like Grafana Mimir, Thanos, and Cortex as well? Now, to understand these techniques, first of all, we have to understand why a query could be slow. And this talk is intentionally oversimplified. We just want to focus on the key concepts, and we are just going to focus on one single query. What's probably the most common query? The sum rate of a metric.
So when we run a query in Prometheus, Grafana Mimir, or Thanos, the first step is always to parse the query. And in particular, we want to find all the instant or range vector selectors. So in this case, for this query, we have the range vector selector, metric, namespace equal app. Then, given our range vector selector, we want to get our label matchers in order to find all the matching series, all the series matching these label matchers. So the way this is look up in storage is first we will look up all the series matching name equal metric, then all the series matching namespace equal app. We intersect the two sets, and the result of the intersection will be our matching series. Then, for each of our matching series, we want to fetch the samples within the queried time range. So in this case, our samples will be our data points, our value timestamp pairs, such as we have here. Once we fetch all of our samples, we will process them. So we will run the query. In this case, we will run the sum rate over all the samples of our matching series. And just a note that this process is done sequentially because the PromQL engine is single-threaded. Once the query completed, we can send the result back to the client, which can be Grafana or, for instance, a Prometheus UI.
Where is the time actually spent, in this process? Well, the answer is it depends. It depends on the query you run. It depends on the label matchers, whether it's a high cardinality query or not. When I talk about high cardinality query, which is something you will hear a lot here in this talk, I mean the number of the matching series of your label matchers. Like in Grafana, we consider a high cardinality query anything above 50, 100,000 matching series. And it also depends on the system you use. Like in Prometheus, all your historical data is stored on a local disk. If you run Grafana Mimir or Thanos, typically your historical data is stored in object storage, like AWS S3, which has a different latency compared to the local disk. But what we see at Grafana Labs, running Mimir across all our customers, is that roughly the 30% of the time is spent finding the series matching your label matchers and fetching the samples. By fetching the samples, I mean fetching the chunks, which are the compressed samples. And then the 70% of the time is actually spent processing these samples, like decoding the chunks, and then computing the rate and the sum. So that's why, for several optimization techniques, we actually focus more on techniques to reduce the time it takes to process the samples rather to fetch this data. I also would like to share with you what we see being the biggest factors which impact on the query execution time. So when it comes to looking up the series, which again means giving your label matches, finding the matching series, most of the time spent is a function of the query time range, whether we are querying just 1 hour, 1 day, 1 week, 1 month. The actual label matches you use, for example, if you use the not equal or not matching irregular expression, they are less performant due to how TSDB works compared to the equal or matching regular expression. And also the total number of series you have in TSDB. Why? Well, because the rule of thumb is that the more series you have, the bigger the TSDB index of each block is, and typically the bigger the TSDB is, for many label matchers, it's a little bit slower to query the index. But when it comes to fetching the actual data and processing the samples, what we see is that the time spent is mostly dependent on the actual number of matching series, whether it's just matching 1 single series or 1 million series. That's completely different. And the actual number of processed sample. I would like to focus on processed sample, because that's actually what we see being probably the biggest impact. What do I mean by processed sample? Let me show you through an example. We have our sum rate query, and we run this query as an instant query, which is evaluated at a given point in time. Let's say this query matches 10,000 series, and we have a time interval of 5 minutes in the query. And again, let's do another assumption, that you configure Prometheus or the agent with 30 seconds scrape interval. So over the 5-minute time interval, you have 10 samples. The total number of samples we have to fetch from the storage and process is 10,000, which is the number of series, multiplied per 10 samples per series, so 100K. Now let's run the same exact query, but as a range query. When you run this as a range query, we have to compute, basically you have to evaluate this query for every step. The step is basically, for each timestamp in output of your query. Now, if you run this query over the last 6 hours in Grafana, the number of steps requested by Grafana is 1,400. So since each sample needs to be processed multiple times, basically within the time interval falling within the given step, 5-minute time interval, the total number of samples to process is actually the previous number, 100K, multiplied per the number of steps we have in the query, which is 1,400. So it's 144 million samples to process, which is way bigger than the previous one, right? Again, it's very fast to run, to process 100 million samples in PromQL, but sometimes we see some wild queries. And just as an example, if you, instead of 5 minutes, you put a bigger time interval in your range query, the number of samples to process just linearly increase. If instead of 5 minutes you put 24 hours, the number of samples to process to iterate over and over, it's 41 billion. And what we see is that the time it takes to process the sample nearly linearly increase with the number of samples to process. So that's something to keep in mind when you're going to run your next range query.
So in highly scalable and distributed systems such as Grafana Mimir and Thanos, it's actually very easy to write high cardinality queries. So as you see, queries that can touch over billions of samples, and we as users expect these results to be quite fast. We want them fast. So in this section, we will be talking about some of the fast query performance techniques that are used in Grafana Mimir and in Thanos. So let's assume that you have a dashboard with a panel with this range query over the last 6 hours. So when the panel loads for the first time, it will execute the query, and it will have to process all the samples from the last 6 hours up until now. But then we can store this result in cache. However, due to possible delays on the remote write, we never actually cache the last 10 minutes of data. So that means that the next time the panel refreshes, we will run the query again, but this time only the last 10 minutes of data, the samples corresponding to those 10 minutes of data are actually processed by the PromQL engine. The rest of the remaining portion of the query can actually be fetched from cache. So this means that with this technique, we are able to cache query results and get them subsequently. So, for instance, if we have an incomplete cache query result, such as is this case, we just need to calculate the required partial query, in this case the last 10 minutes, and execute them separately. Then we just need to merge the result back with what's in cache and send it back to the client. So these are some of our benchmarking results that we see in Grafana Cloud for all of our customers in production. And we see that around 40% of our range queries are cacheable. Of this 40%, we have a 92% cache hit ratio with around a 5 millisecond cache lookup latency. So this technique is probably the best and the most effective optimization possible because basically we are just fetching the results from cache. We don't need to run the code. And all the future requests will be a lot faster. But the thing is that this doesn't apply to first-time queries. So a query can only benefit from this if its time range interval was already processed by a previous query. It also requires queries to have the start and the end aligned to the step. This is because, as you know, time is a moving window, so we need to store the query results in fixed time blocks in order to increase the cacheability of the results. And this is actually the only way that we can store the results with accuracy. But if you use Grafana, you don't have to worry about this. It does automatically for you. Again, the last 10 minutes of data are never cached. This is because these are push-based systems, so it's always possible that with remote write, we don't have the most up-to-date data right now. And it only applies to range queries. So let's now assume that we have the same query, the same range query, but instead of the last 6 hours, it's spanning the last 3 days. So basically, it will have to process the samples from the last 3 days up until now. And this is a very simplified overview of the steps that we showed previously on the query execution workflow. And first, we will parse the query, then we will process the query sequentially, and we will send back the response. So we cannot, and we don't want to parallelize the first and the last steps, but we are able to parallelize the step that takes most of the time, so processing the query. And this is how we can do it. So we can split a multi-day query into multiple partial one-day queries that can be executed in parallel. So in our case, we will still parse our query, our last range query over the last 3 days. We will split it into 3 partial queries, each one with 1 day time range interval. All of these partial queries will be executed in parallel concurrently. Once they all finish, we merge their partial results into a single result, which is then sent back to the client. And as you can see here from the graph below, the execution time is reduced significantly. So some of the, again, benchmarking results that we see in Grafana Cloud is that around 10% of our range queries get split by time. Of these multi-day range queries, we see that on average the time range interval is 7 days. And we also observe the query latency reduction of 75% on multi-day range queries. So this technique, unlike with the query results caching, it works with any range query, including first-time queries. However, it only applies to queries spanning multiple split intervals. In our example, it was based on 1 day, but this is configurable. So this means that if we get a query with a time range interval of less than 1 day, we would not be able to split it. And again, it only applies to range queries. So What about instant queries? It's also very common for us to have instant queries where the instant vector selector, the time range on the instant vector selector is quite high. So in this case, the value in brackets, the 24 hours. And in here we have a slightly different query than the sum rate. We have a sum max over time, and I'll explain you why in a couple of slides. But here the process is exactly the same. So in here we will have to process the last 24-hour samples of data up until now. And we have the same sequential steps. So how can we parallelize these steps, the processing of the query sequentially? In Mimir, we recently introduced an experimental feature where we are able to split instant query into multiple partial queries by using the offset operator. So in our case, we have the sum max over time over 24 hours. And we can split it with a split interval of 6 hours into 4 partial queries, each one composing the 6 hours, interval of 6 hours. So this means that the first, for instance, the first partial query from now, it will take into account the last 6 hours of data. The second partial query will do an offset of 6 hours and then look at those 6 hours and so on and so forth. And we can see that, again, we are able to parallelize all of these partial queries in parallel, similar to what we saw on the range query with time splitting. However, there's a limitation to this feature that affects the correctness of rate, increase, and delta. And this is why we use the max over time instead of the rate. So this is because composability is not a guaranteed property in PromQL. So this means that the rate over the last 12 hours is not the same as the sum of 2 rates over the 6 hours. Because basically the two samples, the two intervals, the difference between the two intervals is not taken into account. So for instance, just to clarify in this graph, if you look into the first interval between the 0 and the 4 hours, it has a very slight increase, and the same happens between the 6 and the 12 hours. However, if you look at the sample immediately before the 6 hours and the sample immediately after the 6 hours, we see that there is a very high increase that is not taken into account when we do this sum over rate.
Now, the techniques we've seen so far are all about partitioning the workload by the time dimension. But actually, there's another dimension we can partition on, which are the series. And that's basically the main idea behind query sharding, or I think in Thanos it's called vertical query sharding. And the idea of query sharding is to partition your query by series. So we have our sum rate query. And this query can be split into multiple partial queries. In this example, 3 shards, but we can run with any number of shards. And each partial query processes a different subset of the series. Like with 3 shards, each partial query processes roughly the 33% of series each. These partial queries are, again, executed concurrently. And then we rerun an aggregation on top of the result. We keep showing, the sum rate, but this works with the sum by labels, sum without labels, minimum, maximum. We also made it work with the average. We basically rewrite the average as a sum divided by count. So we slightly rewrite the query to make it work. But that's basically the main idea behind query sharding. Now, query sharding works both with instant and range queries, and we are using it in production at Grafana Cloud since several months. What we see across all our customers' queries is that 68% of the queries are actually shardable. The reason why there are some queries which are not shardable is because not every single PromQL function can be sharded. I don't know, standard deviation, we can't shard it. We can't push it down. Among the high cardinality queries, which are sharded, we see a query latency reduction between 2 and 10x. And the biggest gain we see is for instant queries with large time durations in the vector selector. And the reason is basically because this technique is very effective when it comes to parallelize the samples processing.
So how do we do query time splitting and query sharding come together? Well, it's actually quite simple. We can combine these two techniques and use them both in instant and range queries. We'll look up for the range query example, just for simplicity. So basically, we will first split our query over the range interval of 3 days. So we will split it into 3 partial queries. And then each one of these partial queries will be further split into multiple partial sharded queries. In this case, with a sharding factor of 3, we will have 3 queries for each day. So this means that in the end, we can split this query into 9 partial queries, where each one of these partial queries can be executed in parallel, and all of them will be looking into specific parts of the data.
In this talk, we just shared the key ideas of 3 main techniques we use, both in Mimir and Thanos. There are some implementation differences between the 2 projects, but the idea is shared between the 2 projects. Both projects and other projects we didn't cover use other techniques as well. I don't know. Both Mimir and Thanos have several layers of caching. Thanos support downsampling as well. If you think about downsampling, it's yet another way to reduce the number of samples you have to process in your query. That's all about it. Or in Mimir, when it comes to query sharding, we also shard at the storage level. So basically, we are able to map the shards into different TSDB blocks. So when we query a given shard, all the series for that shard is in a dedicated TSDB block. This is an optional feature we have in Mimir. What's about the future? Well, both communities have a bunch of ideas. So keep watching, because Bartek and Philip will share something very cool next. I would like to share a couple of ideas that we keep thinking about in Mimir. We think that with the experimental instant query result time splitting, we may be able to cache the result of the partial queries if we align them to time boundaries. Another idea we are talking since a long time, and sooner or later I will build it, is a sort of query planner. Basically, I would like to collect statistics about all the metrics we ingest and the queries we run, and then use these statistics to better plan the query execution, like how many time intervals to use, how many shards, which technique should we use in order to squeeze out the performance of the query. And that's all. I know this talk was a little bit concentrated, so if you want to get the slides and watch them again offline, there's a QR code.
So I'm guessing there will be questions. Who's one here? Okay.
Hello, thanks for the talk. I was wondering, now that we will have out-of-order sample support, will that change the caching? And yeah.
Yes, it does. Out-of-order support is a complication for caching. Right now, it's not handled very well. So the hack or the workaround is that if you configure out-of-order time window to an hour, you can configure Mimir to not cache the last hour of data. This may work if you have a short out-of-order time window, like 10 minutes, 1 hour, 2 hours maybe. Doesn't work if you want to ingest any sample with any timestamp for real. What we are brainstorming, but we haven't built yet, is a caching validation when we ingest out-of-order samples. The typical use case we see with out-of-order ingestion, at least given our customer use cases, is that the stream of out-of-order samples is not constant over time. We're not just ingesting, 1 millionth of out-of-order samples per second. Sometimes we have some spikes in out-of-order ingestion, and then for a few hours there's nothing ingested out-of-order. So, caching validation may work. But yeah, that's a good question. We should have included in the slides. We will update the slides. Thanks.
All right, more questions. One at the back here.
Do you think these techniques are only useful for things like Mimir, or would they be useful or possible in Prometheus itself?
I'm not part of Prometheus maintainers, so I can't speak for Prometheus. My experience with Prometheus is that so far they've been quite focused on getting Prometheus working very well, but running the query as a single core, so basically not scaling out the query execution either to multiple cores or even as a distributed system on multiple machines. The query result caching is implemented in a dedicated component, both in Cortex, Mimir, and Mimir, which is called the query frontend. And the query frontend, both in Cortex and Mimir, can run as a standalone component that you can run, if you want, in front of Prometheus. So basically, you, instead of running your queries against Prometheus, you run your query against the query frontend, and then the query frontend runs the query against Prometheus, cache the result, and returns back the result. Query sharding query sharding, it's something which is deeply coupled with how both Mimir and Thanos work. So it's not something you can get out of the box from Prometheus.
Hi, thanks for the talk. My question is about this query shard factor in Mimir particularly. Can this shard factor be dynamic? Currently, can Mimir figure out based on how many workers available and figure out this shard factor dynamically? Or is it like static where you have to go and configure? Yeah.
Good question. It's dynamic. And the main reason why it's dynamic is because when you both apply the time splitting and the query sharding, you may end up with an explosion of partial queries. So think about, instead of running the last 3 days query, you run the last year query. So split 1 day queries, 365 queries. And then maybe you also shard by a factor of 8 or 16. So you have thousands of queries to run. I mean, it would be even way slower than just running the query as is without any optimization at all. So we dynamically compute the number of shards to use based on, right now, based on the time range of the query and the portion of the query which have not been cached yet. So if you run a query, I don't know, over the last 3 days, and the last 2 days of query are actually picked up from the cache, we have just run the last 1 day of query, so we can run at full parallelization with the query shard. But if the last 3 days of queries are not cached, we reduce the number of shards for each daily query so that the total number of partial queries we run is nearly constant. However, we can do better, and that's why I'm quite keen on the query planner. Because the missing information we have right now is, before running the query, knowing how many matching series the query will have. Is it going to be an high cardinality query or a very low cardinality query? Well, unfortunately, we don't know yet. And that's why I would like to know, because we would be able to take better decisions before running the query. So, picking up the right number of shards in order to squeeze out the best performance without overloading the system, with an overscheduling of many queries you just don't need.
All right, any more? Okay, I'm not seeing anyone.
Thank you. Good job.